Hey there, educators. If your child or the students in your classroom are struggling with multiplication facts, I want to share something that was created specifically to build understanding. The Seeing Patterns Building Power series is designed to help students make sense of multiplication before we ever rush to memorization. Two books are currently available on Amazon: Seeing Double, Making Sense of Two Equal Groups, and Seeing Nothing, Seeing the Same, and Seeing More, Making Sense of Multiplication with 0, 1, and 3. These books aren't drill sheets disguised as stories. They're visual, conceptual experiences that help students see structure, recognize patterns, and build fluency in a way that sticks. Because when multiplication facts become automatic through understanding, students free up their cognitive load for more advanced topics like ratios, algebra, functions, and modeling. Fluency becomes a foundation and not a hurdle. You can find both books now on Amazon. Just search the titles or my name to grab your copies. And one more thing I am especially proud of: my 16-year-old son recently released his first book, Anansi, Shadows of Myth and Mystery. If you have a reader who loves adventure, mythology, and a little bit of mayhem, this is a story they'll want to dive into. Support young mathematicians, support young authors, and let's keep building power one page at a time. Hey there, educators, and welcome back to the Make Math Happen podcast. I'm your host, Lanisha, and today we are wrapping up our month on connecting math. Over the last 4 weeks, we've talked about ratios as relationships. Dr. Pam Harris, in Developing Mathematical Reasoning, reminds us that ratios are about how two quantities vary in tandem. When one changes, the other changes in a predictable way. We took that a step further by looking at the relationships between two parts, the relationship between a part and its whole, unit reasoning, and reciprocal thinking. Last week, we zoomed in on proportionality, which really is the heart of sixth grade without the formal language. Here, we discussed the representations that make proportionality visible and how critical those representations are to students understanding what proportionality means. Our work didn't start with ratios, though. Back in December, the conversation started with spatial reasoning. I posited that geometry is the perfect place to start in middle school because it allows students to recall attributes of figures they work with in primary school. That recall builds a foundation from which to draw when we move into units on number systems and ratios and proportions. Geometry itself is visible, and it allows us to make other domains visible as well. We can use area models to multiply multi-digit numbers, emphasizing number composition, length, and place value. We can use double number lines to represent percent problems, emphasizing parts, wholes, distance, scale, magnitude, and all the other relationships therein. If you zoom out and look at the last 3 months, a pattern emerges. Geometry gave students structure, number systems gave students magnitude, ratios gave students relationship. And today's episode is about the bridge, because proportional reasoning is not our end goal, it's preparation for modeling. When students understand proportional relationships deeply, something powerful happens. Tables become coordinate pairs, unit rates become slope, double number lines become graph, scaling becomes similarity. Proportional reasoning becomes linear thinking. When a relationship is proportional, we can represent it as a ratio table, a tape diagram, a number line, a straight line through the origin, and eventually a rule or an equation. In these various representations is the convergence of geometry, number systems, and ratios, and that intersection makes modeling possible. Modeling is simply representing relationships in a way that allows us to analyze and predict. The bridge from ratios to functions is not just about linear equations. It's really about relationships. And more specifically, it's seeing patterns in how quantities vary together. If we look at the vertical progression across grades, this isn't new work that suddenly appears in middle school. In K2, students are counting, comparing, describing more and less, representing quantities as positions on a number line, and understanding addition as putting together and subtraction as taking things apart. That's relational thinking. In grades 3-5, students identify and explain patterns in arithmetic. They develop understanding of fractions as numbers. They analyze patterns and relationships. They graph points on the coordinate plane. They connect multiplication to area and scaling. That's relational thinking expanding. By grade 6, students understand ratio concepts. They represent quantitative relationships between dependent and independent variables. And in grade 7, students are now analyzing proportional relationships. By the time they make it to grade 8, we want students to understand the connections between proportional relationships, lines, and linear equations. We also want them to define and use functions to model relationships between those quantities. Notice the thread here. It's not computation. It's not procedure. It's relationships over time. If we zoom in on what a function actually is, it is the relationship where each input is paired with exactly one output. But if we leave it there, students are memorizing words without understanding structure. So when I teach this idea, I don't start with notation. I start with a recipe. Think about a chocolate cake. If you follow that recipe exactly, same ingredients, same quantities, same ratios, can you accidentally produce a lemon pound cake? No. And why is that? Because the ingredients and quantities are in a fixed relationship. If I input 2 cups of flour, 1 cup of sugar, 2 eggs, and 3/4 cup of cocoa powder, the output is predictable, chocolate cake. If I double every ingredient consistently, I get more chocolate cake, but it's still chocolate cake. The output changes in size, but not in identity. That's functional thinking. Each input combination produces exactly one output. Not sometimes, not maybe, exactly one. And this isn't about memorizing a definition, it's about understanding how ingredients work together, how quantities vary in tandem, how changing one quantity affects another, how stable relationships produce predictable results. Students have been doing this kind of thinking in ratio units. If 2 cups of flour require 3 cups of sugar, and I scale the flour, the sugar must scale in proportion. That's multiplicative structure. That's pattern recognition. That's relationship thinking. And that's the conceptual groundwork for functions. Because a function is simply a formal way of saying when one quantity changes, the other changes in a consistent and predictable way. Before students ever graph y equals 3x, they should see that as flour doubles, sugar doubles. As distance increases at a constant speed, time increases predictably. As one variable grows, the other responds in a stable way. Functions don't appear out of nowhere in 8th grade. They are the natural continuation of proportional reasoning. Ratios train students to see relationships. Proportional reasoning trains students to see stable multiplicative patterns. Functions formalize those patterns. And when students understand that not just the words, but the structure, linear equations stop feeling like a new topic. They feel like the next chapter in the same story. But here's where this becomes instructional and not just conceptual. If relationships build over time, then our expectations for students' thinking must also build over time. In a previous episode, I processed the idea of whether evidence of student thinking should look exactly like ours or whether there should be a variation. After listening to a recent episode of Chalk and Talk, I've refined my thinking a little. There are times when students' thinking should look very similar to ours, and that's during the acquisition phase. During acquisition, students are building something new. They are learning vocabulary, they are learning representations, they are learning ways of thinking that may not feel natural. At this stage, alignment with the teacher model is appropriate. Acquisition aligns closely with what John Hattie describes as surface learning. Surface learning is not shallow learning. It is foundational learning. It is where students are learning those new concepts. They're building that background knowledge. They're developing those initial procedures. They begin to form accurate mental models. In this phase, clarity matters. Modeling matters. Worked examples matter. Guided practice matters. Students' work may look similar because they are internalizing structure. But learning does not stop at the surface. As students move beyond acquisition, they enter what Hattie describes as deep learning. Deep learning is where students connect ideas, they're comparing strategies, they're explaining patterns, they're justifying their reasoning, they notice structure across problems. This aligns with what we might call fluency and generalization. Here, student thinking begins to show variation, not because they are confused, but because they are connecting. And then comes transfer learning. Transfer learning aligns with adaptation. This is when students apply ideas in new contexts, select strategies independently, combine representations, make the math their own. At this stage, if every student's work looks identical to yours, to mine, to the teacher's model, something may actually be missing because adaptation is where ownership shows up. So the progression matters. Surface learning builds stability, deep learning builds connection, transfer learning builds independence. And if we think about the domains we've explored, geometry supported surface and deep learning by helping students see structure. Number systems built magnitude and flexibility. Ratios develop relationship thinking. Proportional reasoning strengthens deep learning. Modeling requires transfer. So when we see variation in student work, the question is not, why didn't they do it my way? The question really is, what phase of learning are the students in? Because evidence of thinking should evolve over time, not immediately, not randomly, but developmentally. And that understanding changes how we respond in the classroom. So, where does this leave us? Proportional reasoning sets up modeling. Modeling requires students to represent relationships, interpret variables, analyze change, predict outcomes. And that only works if geometry gave students structure, right? We need them to see it. Number systems gave them the magnitude, right? How big is this? Ratios gave them variation. What is the change there? How are they different? Modeling is the convergence, okay? So here's the big idea as we close connecting math. Ratios were never the destination, they were preparation. If students can see structure, if they can understand magnitude, if they can recognize the variation and adapt strategies, they are ready. They are ready. So next month, we are moving into modeling math. And modeling is where students begin to use mathematics to understand the world. It is the same story. It's just a deeper transfer. So I'll see you soon.